record, right? Hopefully, so I just show you with the green laser. This is different color laser, of course. So it's the same pattern, right? Where you have a bright, right? And they're equally spaced apart because we're doing a double slit the light is passing through a double slit as opposed to more slits, okay? And we're going to do today, we're going to go to more slits, okay? Why only do two, right? So these are known as diffraction grating. So outside of like a lab experiment, such as the ones I set up here, usually you don't have this double slit situation, right? Usually you actually have multiple light sources that are interfering with each other. For example, right, so if you have clouds in the sky, those basically are like kind of like little slits where, you know, some of the light can pass through, but then if it hits a water molecule, that water molecule will absorb the light, and then so you have these, you know, millions and millions of slit situation in the sky, right? And you actually create these patterns in the sky where, you know, the different wavelengths of light. So for example, the yellow wavelength here, right, gets refracted less, diffracted less because this, you know, imagine the sunlight is coming from behind here, right? As the sunlight comes, oops, that's a bad color for this drawing. Let's do green, okay? Right, the yellow will diffract less, but then the red actually diffracts more, right? And that's following exactly the equation that we just used, which is that y is the m of the bright spots are, let's do the bright fringes, right? That's the one without the 1/2, right? It's lambda times L divided by D, right? So the higher the wavelength, right? For example, red light has a higher wavelength than yellow light, right? Therefore, it actually bends more when you go through these double slits, right? And that's why you see the red clouds up here and the more yellowish cloud down here, because the red light has a higher wavelength than the yellow, right? Same thing happens if you just go on the, after it rains, if you see a little oil slick on the ground, this is actually many slits, double slit, combined together to make these rainbow colored pattern for you, okay? And we're going to describe how we're going to deal with these many slit situation, and these are known as what's called diffraction grating, okay? This little word here, okay? There's actually one sitting there. I can show you guys that after lecture if you have time, okay? So instead of dealing with just a single double slit, right now we have many of these slits added up together, okay? And things get a little bit more complicated, right? Because instead of just two different electromagnetic waves interfering with each other, you have many different waves interfering with at the same spot, okay? So, but the same equation that we derived last time can be used where, remember that this is basically delta R, right? The difference in distance, oh, that's a very bad R, difference in distance, right? It's just d sine theta m, right? That's just by drawing a triangle, right? You just, if you know how to draw a triangle, you can derive this equation, right? And then in the diffraction grating case, right, we are not going to make the small angle approximation because for diffraction grating, some of the angles might be big, some of the angle might be small, right? You cannot make that approximation anymore, okay? Right? So if you continue on without the approximation, what you will find is that y's of m, meaning the position where you see the bright and dark spots, right? Let's say you have the central position here, right? This is y's of m equals to 0, y's of m equals to 1, y's of m equals to 2, and so on like that, right? It also goes negative, right? Y of m equals to 1 also down here, right? Right, all these positions can be calculated by just plugging in what the theta m is. It turns into a more complicated equation because like you have an angle inside another trig function. Now you have to plug that angle into a different trig equation, right? We're going to play around with this in a little bit, okay? So what happened is that instead of getting spacing between the bright and dark spot that we saw that are exactly the same, what happens is that the central maximum will still be in the middle, okay? And then the next bright spot will be a little bit further away, but then m equals to 2 will actually be much further away, okay? It actually grows as basically a sine function, right? Because we're no longer be able to make this approximation of sine of theta being a small value. Therefore, you can just, make the approximation that sine of theta is basically approximately theta, right? So let's see what happens when we do this, okay? So if we were to figure out, let's see what we're going to do. If we want to figure out this function, right, where y to m is, right, as a function of basically all the other variables, what we need to do is solve this equation up here for thetas of m first, right? So if I copy down the equation, right, thetas of m equals to m lambda, right? I want to solve this for thetas of m, right, m lambda divided by d. Since this is a sine function, I do an inverse sine of both sides, right, in order to get the theta out. So thetas of m is actually the inverse sine function of m lambda divided by d, okay? So this gets a little bit hairy, okay, because of all these inverse trig function. Now what we're going to do is we plug that in here, okay? And so y to m is actually L times the tangent of the inverse sine of m lambda over d, okay? And this turns into basically a inverse trig function buried inside another trig function, right? But all of this you can punch into a calculator and actually calculate, okay? And this is the reason why instead of the spacing being the same, right, as you increase m, it actually gets spaced out more and more. So m equals to 3 will be all the way up here, okay? Because it actually grows as like a tangent function, okay? All right. And then another interesting thing is that, right, this dependence in here, right, how far the bright fringes are located from the central value, right, is bigger if lambda is bigger, right? If lambda goes bigger, right, this value also gets bigger, right? Because you're taking the inverse sine of it and then taking a tangent function of it. So what happened is that, right, if you have two different light sources, let's say you got a purple light and a blue light, okay? The blue light, okay, has a longer wavelength, and therefore, right, the y is at m for blue, right, or another word, longer blue light, right, another word, longer wavelength, right, is going to be larger, right, where the purple, right, has a slightly shorter wavelength, right, therefore it doesn't get bent as much, okay? Sorry, the y to m is not as big, right? And you can see that in the dependence here, right? Over here, right? As lambda gets bigger, right, all these y's and m just get spaced out more, okay? All right, so you can make a diffraction grating, right, simply basically by having a piece of glass and just kind of cutting into it, right? And this is like kind of a zoom in view of a diffraction grating. There's actually one sitting on that table right now, where these are the part that blocks the light, and then you just have slits that kind of allows the light to pass through, okay? And the width of these things has to be something on the order of a micrometer. Otherwise, it will not create the interference pattern that we want. And we're gonna see maybe tomorrow actually why it has to be that length for it to happen, okay? Right. So let's do a quick example where, let's say we're doing some sort of, we have some sodium lamp. We actually have one in the back there. I could have brought it out, right? And it passes through a diffraction grating that has 100 slit per millimeter, okay? That means if you go up a millimeter here, right, there'll be 100 slits, okay? Right? So that's going to be important because we're going to try and figure out, well, what does that translate to in the equation that we just derived. In fact, what I'm going to do is I'm going to rewrite that equation before I forget it, right? L times the tangent of the inverse sine of m lambda over d right? This complicated equation up here, okay? In fact, I'm going to bring my calculator out because I'm going to use that in a second, okay? So in the setup, right, we're going to say that while the diffraction grating has 100 slits per millimeter, okay, so that's some sort of information. I'm not sure what it relates to here yet, okay? The screen is 1 meter away, so well, that, obviously that's going to be L, okay? And then the two bright yellow fringes are visible at these distances, okay? That means there are two different Y's of M's, okay? And these fringes are this distance away from the central maximum, right? If you go back up to the picture up here, right? The central maximum is here, right? If you're looking at these two fringes, that means M equals to what? M equals to, well, if this is M equals to 0, this will be M equals to what? 1, right? Exactly. So that means M is actually equals to 1, right? But there's two different lights, right? So let's call that lambda 1, right? That's going to be 72 point. Now let's convert that to meters. So I don't have to deal with the unit conversions, okay? And then y sub the other one, right, is also M equals to 1, right? It's just a different wavelength of light. It's like the purple light versus the blue light, okay? Lambda 2, right, that's 0.7300 meters, okay? So it seems like we're going to be able to we want to figure out what lambda is, right? That's what we're trying to figure out. We don't know what D is. We know what L is. Well, we can punch in trig functions into our calculator, right? We have all the different M's, right? But how do we figure out what D is? Anyone have an idea? Well, I change my calculator to radiant mode. Anyone have a suggestion? I'm sorry? So remember D is the distance between the slits, right? So how will we figure that out? It's not the difference between the bright spots, right? Okay, so if we have a diffraction grating like this and want to figure out the distance D between here, how do we figure that out? If we know that there's going to be 1,000 slit per millimeter. Yeah, Alex? The distance would be the 1,000 by okay, let's do this by drawing, right? You know how I love drawing, right? So we have this the diffraction grating. If you take a millimeter of it, they're saying that there's going to be 1,000 slits in it, right? So the width of each of these individual slits, which is actually the D that we want, right, should be this 1 millimeter, right, divided by the number of slits, right? Okay, right. So just as if you have something that's 1 meter long, right, and you divide, and I say, oh, divide it by 100, right, there'll be 1/100th of a meter, right? Okay, so D is actually, right, 1 millimeter divided by 1,000. In other words, it's going to be 10 times 10 to the negative 6 meters. Okay, so I'm just going to do this is 10 to the negative 3, right? Okay, so we have everything. Now it's just, plugging in and then doing calculations, right? So therefore, just to solve the problem, right, we're going to say that, well, y is of m, let's call this m of lambda 1, right? That's going to be equal to this, right? And we're solving for the wavelength. That's going to be interesting because we're going to have to invert all of these functions. Okay, so we're trying to get to the wavelength. Okay, so therefore it's y. I'm just going to write y instead of all these subscripts. Okay, divide by L. Right, that's actually the tangent of it because I divide both sides of that. So I have to do the inverse tangent of both sides, right? That'll get rid of the tangent function. So now we have the inverse sine equal to some other function, right? And then to reverse the inverse sine, you just do the sine function, right? So you take the sine of both sides, right? And that'll get you to the point where you have, I'm going to put the stuff on the right, on the left here, And the stuff on the left is going to be sine of the inverse tangent of y over L, right? And if I want to figure out what lambda is just going to be d over m. Well, m is 1, right? So we don't actually need that, okay? D times this complicated multi-layer trig function, right? Y over L, okay? So for wavelength number 1, right, y is the 0.7288, right? So let's punch that in and see if we can get something reasonable, right? So it should be something on the order of a few hundred nanometers, okay? So D is, what the heck was D? D is 10 to the minus 6, okay? I'm gonna take the sine and then take the inverse tangent, which is this green function here, okay? And y is 0.7288, and the length is 1 meter, so that's nice. We don't have to divide by 1, okay? So lambda 1 is gonna be 589 nanometers, okay? So that's a reasonable wavelength of light. If we plug in, right, 7300 here instead, let's see what wavelength we get. Okay, then lambda 2 is actually 590 nanometers. So these two wavelengths are actually just 1 nanometers apart. We're actually able to see that by just applying a diffraction grating to it and measuring the difference on the order of a millimeter, okay? In fact, you can actually see this, okay? These are the spectrum of a sodium lamp, right? And the wavelength we were seeing was 590-ish, right? So it's around here. Oops, that's 580. So it should be around here. So if you go up, you see that. These are the two wavelengths we were actually looking at, okay? There's actually other wavelengths also that you can see, but you know this problem only dealt with the, those two. Okay. All right. So the hardest thing in these problems is figuring out what D's are, what lambda is, what L is, right? So be really careful about what, because the problem's not going to tell you, oh, D equals to that, right? Because it's going to be, oh, we have some diffraction grating that's this size, right? And you have to figure out what D is, okay? Any question? Mm-hmm. Okay. So maybe I can just quickly talk about why do these oil slick on the ground mix rainbow, right? So one of the things we noted was that different wavelengths of light gets diffracted at different angle, right? Sorry, the Y's and M's of different wavelengths are at different angles, right? So what's actually happened when there's oil on the ground with on top of water is that the ground is not exactly flat, right? So what happened is that the ground, oh, let me just draw that in black maybe, okay? So let's say the ground is this jaggedy stuff, right? You know, right? What happened is that if you have if you have water, right, the water is going to kind of fill out this area here, right? The oil, let's do that in purple, right? It's going to lie on top of it, okay? What happened is that as the light comes in, right, it's actually going to bounce off these little, oh, well, it's going to bounce the other way on this case, right? It's going to bounce off here, right? And all of these, basically, the roughness of the ground becomes a diffraction grating. Okay, technically it's more of a reflective grating, right? Because you're reflecting off instead. Okay, and this is what we're going to cover next. So instead of having the light pass through, right, we're up here, where the light actually passes through and then they interfere with each other like that, right? You can actually have the light just reflect, right? If you have a mirror, right, where you have a bunch of jagged edges, right, what will happen is that if you have light coming in here, right, these light will actually get the interference will create Y's of M's of bright and dark spots at different positions depending on the color of the light, right? Depending on the wavelength of light. Remember there was this complicated equation here, right? It was L tangent inverse sine, right, m lambda divided by d, right? So the bigger the wavelength, right, the further the 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 bright fringes will be located, right? The shorter the wavelengths, for example, blue light will have a shorter, will have a smaller WISA M's, and therefore that's why the colors get separated, right? When you just have the water and oil on the ground, it actually separates the different colors. Okay, that way you can actually see different colors, and that's why it looks like rainbow on the ground when you have just oil on the ground. Okay. This also happens not just in oil on the ground. The protein on our skin called melanin is actually used to actually reflect light, and it reflects light at different amount, right? And this is actually used in, for example, if you take a feather of a bird, right? There's actually melanin in it, and these melanin actually reflect the light at different wavelengths at different WISA M, and separating the different colors. So therefore, you actually have these kind of cool multicolor pattern on a single feather. Okay. Let's wrap up today early. I think we're not going to do single slit today. So let's just wrap up with this stop to think exercise. So let's say we have white light that passes through a diffraction grating and forms a rainbow pattern, right? Remember, white light is actually all the different wavelengths of light combined together. It looks like white to us, okay? So if that was to happen, what would you see on the other side? Would the red be on the right side, and then the purple, which is the shorter wavelength, be on the right, on the left? Or is it the other way, right? That's B. Or are the red going to be the closest to the center, right, where the purple is going to be spread further apart? Or is the red light going to be spread furthest apart, and then the purple will be the closest together? Okay. While you guys think about that, I'm going to draw my little diffraction grating situation and then see if we can figure out how that works. Okay, so we have white light coming in. Let's do this as just white light, right, coming in, and it's creating all these little ripples everywhere, right? Okay. What you're going to see on the screen is some diffraction grating, right? So there'll be a bright spot in the middle no matter what, right? Both purple and red will happen in the middle. So how should I draw the red ones compared to the purple ones? If the red one is here, let's say, right, where would the purple one be? Further away? It'll be close, right? Purple has the shorter wavelength, right? Yeah. So purple has a shorter wavelength, so it'll be closer together. So therefore, the pattern you will see, right, is actually, right, the red fringes are further apart, and then the purple ones are closer together, okay? So that's all we have time for today, and hopefully we'll finish this chapter tomorrow somehow.